Good evening, my name is George Hurd, and I bring you greetings on behalf of the Dexter Squibb Lecture Series Committee. We are responsible for selecting the speaker and making arrangements for this lecture series and the associated activities, and I hope you guys really enjoy tonight's lecture. I'd like to acknowledge my fellow members of the Squibb Committee, Bert Holmes, Sally Wozleski, Herman Holt, and the chair for life of the Squibb Committee, Brenda Henderson. This lecture series honours Dexter for his contributions to the chemistry department at UNC Asheville, and you can read some of those highlights in the program. We are privileged to have Dexter and his wife Joanne here with us tonight. Dexter remains a champion of chemistry and, first and foremost, what we call in Australia a great bloke. I saw Dexter last night for the first time in several months. He greeted me with a warm handshake and then sat with me on the balcony and told me a particularly dirty joke. Dexter knows what makes his friends happy, and join me in congratulating Dexter and Joanne Squibb. I'd like to announce that there will be opportunity at the end of this presentation to ask questions, but I do request, since we have the video recording equipment tonight, that you don't ask a question until you've been given a microphone. So we'll remind you of that after this. Okay, so I now pass this microphone over to Bert Holmes, Philip G. Carson Distinguished Chair of Chemistry, who is going to introduce our guest speaker.
Professor Hurd neglected to mention that he's a member of the Squibb Lecture Series Committee as well, so we need to make sure. Okay, thank you. So I first met Angie Stacy about a year ago, and I realized that she would be a wonderful Squibb lecturer, and I also understood that we had 3 or 4 things in common. And you're probably wondering, what are those things that we have in common besides the fact that she's a chemist and I'm a chemist? Well, you see, I'm from Kansas. And if you're from Kansas, the first question you get is, have you walked the Yellow Brick Road? And the second question you get is, where's Toto? And the third question is, where's Dorothy? And you know, I never knew how to answer those questions until today. I now know where Dorothy is. There's Dorothy. Now, at the moment, only 2 of us in the room know who Dorothy really is, but you're beginning to guess who Dorothy really is. That is indeed Dorothy, and to help make that a little clearer, if you look at the profile of Dorothy and our distinguished lecturer a few years ago, you realize it's the same profile. That indeed, this is Dorothy. She now goes by Angie. I'm not quite sure why she changed her name. So
you're in trouble.
Now we're going to begin the serious introduction, okay? So I tried to pick the top 10 things about Dr. Stacy that are not in your program. And so you've got a program that lists a few of her highlights, and I've picked 10 more. So she's a graduate of a liberal arts college, about the same size as UNC Asheville. She is the first female chemist to be tenured and promoted to full professor at Berkeley. And you can imagine then why she is so interested in diversifying chemists nationwide, the chemistry community nationwide. I call her Superwoman, and now why would I do that? Well, she's an accomplished researcher in the laboratory, and tomorrow she'll talk about some of her nanoscience research. But in addition to that, she's an accomplished chemical education researcher, and as far as I know, she's the only person in the nation that is accomplished in both of those research areas. And as you might expect, it's a woman. She's won, all right. She's won the Gavin Olin Medal from the American Chemical Society for distinguished service to chemistry. She's the James Flack Norris Award for Outstanding Achievement in Chemistry. These next ones deal primarily with her research area. She's the Catalyst Award winner for the Chemical Manufacturers Association. She was an NSF Presidential Young Investigator Award, and that's a huge honor that's based upon your research ability. She's an Alfred P. Sloan Fellow for the same basic distinction for being a researcher. She's the Dreyfus Teacher Scholar Award winner for her research. But more importantly to us, she's a very strong proponent of undergraduate research and the importance of diversity in chemistry. As an example of that, if you walk into the chemistry building at Berkeley, you'll see this quote next to her picture. It says, "Since I feel that independent research is often the most rewarding aspect of undergraduate education, I encourage students to participate in research." And that is certainly a mantra that we at UNC Asheville subscribe to. So I give you the S. Dexter Squibb Lecture Series lecturer in chemistry this year, and if she'll join me, I have a few more things to give her.
Oh dear.
Angie? So we have a plaque that we give to the distinguished lecturer, and the plaque says exactly what the overhead says, so you can read it.
Thank you.
We also have a piece of paper for her that I'll give you later, if the lecture's any good. And so it's our privilege, and help me welcome Dr. Angie Stacy from Berkeley as the 14th S. Dexter Squibb Distinguished Lecturer in Chemistry.
Okay. Sure. Well, thank you very much for that introduction. I will begin first by saying what an honor it is to be here in the presence of Dr. and Mrs. Squibb. And I guess I do need to explain the Dorothy story. And if you guys are ever, the students in the audience, ever do anything like that to your professors, passing pictures around, I will get the student who passed that to you, a former student. My first year at UC Berkeley, we had a Christmas play, and they decided they wanted to do Dorothy on the Road to Tenure. And one of my best friends, who was also an assistant professor, was the dog Dodo. And for those of you who know Brad Moore, he was the Great Oz. It was really an incredible show. It was just pre-video. And I will never participate in a Christmas show again. Anyway, it's a real pleasure to be here. Let me just get the other slides up. And just a wonderful department, and it's been such a pleasure to get to know some of the students and the faculty and all of the friends of the department that are here. And what I hope to do today is engage you in thinking about teaching and learning in general, in chemistry in particular, but in general. And I have to correct something that George said, because I do have some places where I'd like to be interactive. So you're just going to have to talk loud, and I'll repeat what you say. I've already gotten agreement from the people who are recording on that. So what I want to talk about is how can we do a better job for our students? How can we engage them better? How can we help them succeed and understand how chemistry is useful in all kinds of areas of their lives and professions and careers that they might go on to? So to begin, I want to ask the following question of you and get you to think for a moment. I've purposefully chosen a lecture hall from one of the first buildings on the Berkeley campus. A couple things you might notice about it. Does it look a whole lot different than this lecture hall? All right, this is 67, 68, so it's something interesting to think about. Looks a little different in terms of, well, they didn't have color back then. Everything was in black and white. But you might notice that the type of students that are there are much more homogeneous, if you can see who they are. And from that time period, and even long before, we have somehow believed that if I talk and you listen, that's what teaching and learning is all about. So now what I want to ask you, and the students can definitely participate in this, what are the assumptions I'm making if I think that's how learning occurs? What are some of the things that are implicit in that I talk, you listen, and that's how you learn? Any thoughts on that? Go ahead.
Everyone can never mind, I lost it.
Oh, okay. Someone else? Go ahead.
They were paying attention.
Yeah, that you're paying attention. Well, that's an important one. What else?
You're awake.
That you're what?
You're awake.
That you're awake, exactly. Go ahead.
That everybody learns the same way.
Oh, everybody learns the same way. What else? Go ahead.
That you have information that they're eager to learn.
Oh, yes, that you might want to know what I have to say. That's right. Go ahead.
That you're the only one who has information to be learned.
I've got it all. I'm the sage, and we just have to open up your brain, and I'll pass it over to you. Right? Anything else that you worry about? Go ahead.
I said the assumption of comprehension.
The assumption of comprehension, and so I'm the perfect communicator. Didn't you know that?
Right.
And all the words I'm saying are actually understandable to you, right? Anything else that? All right, so just so that you can see some of the ones, you've said them, I could add to your list, but there's this implicit idea that if I tell you you're going to learn, and that you're a blank slate, you don't have any prior knowledge. So I'm not building on anything. I'm just throwing stuff out for you to put into your brain. I am a great communicator, and my goals are clear to you. And that you also want to be here, and that you're engaged, and you want to stay awake. So what I want to do by way of introduction is just explore with a couple of fun activities what some of the ways in which we can think differently about learning. Now, you may laugh, but we're going to start by the themes for the seminar being, first, how students' ideas and experiences are important, and we need to know about them, and we need to build on them. Second thing is how contexts and data and observations really help to situate the learning. And then third, how assessments that promote understanding can really make a difference in what the students take away from the class. But to begin with the student ideas and experiences, I'm going to start with children. Right? So all of you, presumably you were all children at one point, so you all understand something about children. So this is about children's ideas about love. And so different children were asked what they thought. So what's the proper age to get married? 84, because at that age you don't have to work anymore and you can spend all your time loving each other in the bedroom. Once I'm in kindergarten, I'm going to find me a wife, says Tom. What do most people do on a date? Well, on the first date, they just tell each other lies, and that usually gets them interested enough to go for a second date. Concerning why love happens between two particular people, this is a chemistry one. No one is sure why it happens, but I heard it has something to do with how you smell. That's why perfume and deodorant are so popular. And on the role of good looks in love, if you want to be loved by someone who isn't already in your family, it doesn't hurt to be beautiful. It isn't always just how you look. Look at me. I'm handsome like anything, and I haven't got anybody to marry me yet. And beauty is skin deep, but how rich you are can last a lifetime. Okay, so first question. How do you think they got these ideas? What are some of the ways that the children got these ideas?
Television.
Television? What else?
Direct observation.
Direct observations, right? Exactly. What else?
Hearing incorrectly.
Hearing incorrectly. So I think the point is, and when you read these children are observing all the time, right? And they have a lot of ideas about what they're observing, and they're drawing conclusions about what they're observing. And that is true of all of us. We are great at observing, we're great at pattern recognition, and we get ideas, develop ideas about the world around us. All right, so if you wanted to change those ideas that these children have, what would you do? I suggest we just bring them all in, sit them down in the lecture hall, and start to talk about the way it really is. Okay? Is that what you would do? No. All right, so what are some of the things that you might try? if you wanted to help children get a broader understanding of this?
Have them talk to people who are married.
They could ask questions. They could talk to people who are married. You could. You should. Now, Dr. Squibb here has an idea that, well, maybe not right away. But you certainly want to guide them for what they're ready to understand, right? So you see, the point is that when you're looking at an issue like this, or if any of you have interacted with teenagers or been teenagers, you understand that parents telling you stuff isn't going to make a difference, right? You have to have experiences. You have to start to develop some understanding yourself. So that's my first big point that I want to tell you about, is that we are not giving our students the opportunity to bring in the knowledge that they have. We're not trying to understand what they already have and then provide experiences to build on that knowledge. As opposed to, you walk into the classroom, you do classroom stuff here, you walk out, and then your life begins. Now, there's one other one that I want to go through with you, and that is the role of the context in which you're learning things, all right? And so here's, actually, before I go to that, I just want to I want to bring this example back to students in the chemistry classroom. So this is an interesting question. Bond energy, for those of you who aren't chemists in the room, has to do with the idea that atoms stay together. It's very important to chemists. We call the connection between atoms bonds. And so there isn't a whole lot more important in chemistry than kind of having a model and an understanding of what a bond is. So here's the question. When a bond breaks, is heat absorbed or released? Now, this is a 50-50 guess, okay? And actually, the students come in from high school with a 50-50 guess. 50 say absorb, 50% say absorb, 50% say released. Okay, so now you think I'm bashing high school teachers. Just wait. Wait till the end of the semester. We do such a great job lecturing at Berkeley that at the end of the semester, fewer students get it correct than at the beginning of the semester. So that's a bit of a problem, and that really, really worried me. And believe me, it wasn't me lecturing. That wouldn't have happened if I were talking. But the person who was lecturing is a very famous chemist, and he said correctly many times that energy is required to break bonds. Okay? So he said it right. It just, whatever he did, didn't evoke that understanding of bond energy. And here's why. So we teach that atoms stick together and you actually have to pull them apart. You need energy to break a bond. That's why molecules are stable. If the opposite were true, I would be standing here in front of you and my bonds would just, every time they broke, they'd be sparking. They'd be throwing energy out. And obviously, I'm not doing that in front of you. But here's what students believe and why students believe it. So students believe just the opposite. And they have very good reasons for believing the opposite. And that's that we get energy from food. Now, what does that sound like? Sounds like you take the food in, it's breaking apart in your stomach, and that's how you can run around, right? Well, in fact, that's not what's happening. It's reacting with oxygen and making CO2 and water, and that's what releases the energy. But that's not evident because you don't even see the CO2, the carbon dioxide and water. Burn paper and wood, right? Nothing's left. It's all gone. So it looks like the wood just broke apart and released all this energy, which is actually not correct. And explosions are examples. And then just a weird idea to leave you with here is that, have you ever considered that we actually launch the space shuttle by taking hydrogen and oxygen and make water? Okay? And so the energy that's released to launch the space shuttle has to do with not the bonds breaking, but making the water molecule. All right? But this is a very hard idea, and so you can see very easily that if you don't pay attention to why students are thinking what they're thinking, that the knowledge that you're throwing out to them just seems like, oh, well, okay, I'll learn it for the test, but it won't stick with me after that. All right, so now I have one last little thing that I want you to look at. Take a look at this set of instructions. It says the procedure is actually quite simple. First, you arrange things into different groups. Of course, one pile may be sufficient depending on how much there is to do. If you have to go somewhere else due to a lack of facilities, that is the next step. Otherwise, you are pretty well set. It is important not to overdo things. That is, it is better to do a few things at once than too many. Can you follow that? You have any idea what that's about? Okay, it's not so well written, but still, what do you think that's about? Some of you are going to be able to guess, but when you first look at it, you can't even remember what you're being asked to do. Any ideas of what the instructions are for? What did you say? Gin rum, solitaire, a solitaire, gin, okay, some kind of card game. Laundry, anything else?
It's pretty close to what we're told about how to form an idea of atoms and molecules in chemistry.
And that's my point, actually. Did you hear? It was a kind of pretty close to the thinking about atoms and molecules in chemistry. So someone up here said laundry, and it is about washing clothes, but how easy is it now that you know it's about washing clothes? Suddenly, you get the idea of making different piles. Even though it's not written that well, the context and the connection to something that you do understand is really important. And up with the person in the back who said this is about chemistry, so here's the joke one. The procedure is not difficult. First, bring water to a state where it has undergone partially a phase transition in which the vapor pressure of the gas that is formed is equal to the pressure of the atmosphere. All right, and you can see how silly this one is. And do you have any idea what this one is, actually? It's making tea, okay? And once you have a context for this, you can see that the first long phrase of words is about boiling water. So what we tried to do first, what I want to tell you about, is a high school chemistry curriculum that we worked on called Living by Chemistry. And the two examples that I've just given you of providing a context, a connection for students to situate the learning, and then second, to create opportunities for students to take a look at data and observations that are strategically put together so that you can look at patterns and you can try to understand what's going on, and make that the way that you take in the information and have discussion and lecture later after you've had an opportunity to get interested. So Living by Chemistry has been out for about 1.5 years, and it's been adopted in a number of high schools across the country. We started by writing teacher materials because really if you want to, lecturing turns out is actually easier. You can just write stuff down and go in the next day. But if you actually want to do things that help students, you actually have to go and observe students and refine the lessons until it starts to work well. And so we spent a lot of time sitting in classrooms. I have graduate students doing research and education, and they would sit in classrooms to try to see what was working and what wasn't. And what we ended up doing was first writing teacher guides so that we have a lesson for every day in the classroom, and these lessons have a goal, they're sequenced, and they have some kind of an activity or way in which the students are first looking at information, gathering information, talking to one another, as opposed to just passively sitting and listening. And I can just give you a really quick flavor of this. We did end up writing a student edition to go along with it, but we divided this into 6 units that provide guided inquiry ideas. It's really written out in a very rich way so that teachers can build off of the foundation that we provide. And we tried in each case to situate the learning to capture student interest. So let me just very quickly run through the 6 units and tell you about their context, and then I'll do a little bit from one of the units with you so you can see the difference between how chemistry is often taught. So the first one is on alchemy. We got some pushback at first when we decided on alchemy. Did that sound like witchcraft? Do chemists really do alchemy? But we really did want to call it alchemy because here's what happens. On the very first day of high school chemistry, the student takes a penny and turns it into gold. Okay? It's a beautiful experiment. So you have a golden penny. Oh, and they are pretty excited about this. All right, but here's the question. Did you make gold? So what do you think the students say? Okay, some say no. Some will say yes because it's the teacher, yes, of course. But there'll always be the person in the back, cap on backwards, slouch down, going, you didn't do that. Because if you did, you would be rich. And you go, that's exactly right. If I could do that, I wouldn't be here teaching and getting this low salary, right? So what a great observation. And that student would normally not even be engaged, let alone making a smart aleck comment like that, wouldn't even be acknowledged. But it's a great observation. Of course I would be making gold pennies if I could. So then the question is, well, what did I make? Could I ever make gold? And we run a whole unit, 6 weeks, where we really explore thoroughly what's the difference between gold and copper, under what conditions could you take copper and make it gold, and what else can you make as a chemist that's really quite valuable. And you see that will take us through matter, atomic structure, and bonding. We then talk about the sense of smell, very popular with high school students, I might add. We had to teach them, though, some nice words because some of the smells are not so nice, and we don't have good language for not so nice smells. So we had to create words for that. So they've all learned the word putrid. That wasn't part of their vocabulary before. So they look here at molecular structure and properties. I'm going to spend a little bit of time on this unit, so I won't say more. But how do we open a bottle of perfume, and how does it get to your nose? How do you know anything happened? What does it tell you, the fact that you don't have to stuff it up your nose in order to detect that it's there? We do one on weather. This is the one where we want them to do a chemistry weather report. So instead of the normal stuff that's on, well, the molecules are moving a bit faster today. Did you notice? So they are exploring phase changes in the behavior of gases. How much is too much? Another popular one. So getting across the idea of a toxin. And obviously here we are not trying to give chemistry a bad name, but everything's toxic. I mean, water's toxic. You can drown in water. So you want to understand how do you measure amounts of substances and then try to assess what kinds of reactions might occur in your body and how toxic they are. And this is where we do stoichiometry, solutions, acids, bases. Fire is my favorite one. So did you know that everything doesn't burn? The high school students don't know that. So they take a whole bunch of stuff and they're allowed to ignite them. And it turns out some of the stuff, like salt, actually doesn't burn. And then other things do. So we start to talk then about, well, what is fire? You start to lose all the magic, unfortunately, when you start to examine these things. But you start to learn what's the yellow stuff and why does it get hot. And so this is a great, fire is a great theme for trying to understand energy transfer. And then we end with a unit called Showtime, where the students actually explore all those beautiful, colorful demonstrations and then learn how they work. Has to do a lot with equilibrium considerations, and then they show their demonstrations to other groups, maybe go to an elementary school. Okay, so with that, I want to just say a little bit about the smells unit so that you can see the style that I'm talking about. So this unit is on molecular structure and properties. How does the nose know? And we walk the students through, we take them through 22 lessons on structural formula, molecular shape, polarity, and we do a little bit with biological molecules. So here's how we start. And I could have done it for you, but after dinner, sometimes smelling these things isn't the best option. So we have 5 little vials here. They all have little cotton balls in them, and they all have drops of odors on them. And we started by just saying you have to choose sweet, minty, or fishy, okay? Because this worked the best in the classrooms to narrow it to this group. So let me show you the outcome. First of all, we'll have a debate. Do you think everybody agrees on this?
No.
No. All right, and that's actually an important part of science. All right? So are we going to go with Bert, who can't smell anything? Or are we going to go with the rest of you who've agreed on what the others are? And so what I would say to the students then in trying to understand what science is all about is your nose is telling me something special. You're actually a very special nose if you were the one who couldn't smell something. But for now, we want to work first on the consensus and try to explore what generalizations we can get from the consensus. And we'll take your special nose into account later when we run into exceptions and things, when we want to understand more. And by the way, people don't even know this. High school students start to then tell their teachers, well, I have smell blindness. That's why I couldn't get my homework done. It actually is something that you wouldn't know whether everyone in this room is actually smelling the same thing. We all have lots of receptor sites in our nose, and if you're missing some of those receptor sites, you may smell something differently or not even smell something that other people can smell. This goes back, you've probably noticed that some people, like my husband, can eat the worst food because I think he just doesn't smell how bad it is. And it has to do with receptors in your nose. But anyway, so we want to go to the consensus. And here's what they come up with, the consensus. These two are minty, these two are sweet, and this one's fishy. Then they go, well, what are they? And then we go, oh, well, I can tell you what they are. Here's the chemical name and the chemical formula. And they all look like, darn, that's not what I was asking. All right. But let me show you what's up there. So this was carefully selected. It's only 5 molecules. Take a look. Look at the names and look at the formulas. And high school students have no trouble listing patterns. Often, people who know more chemistry have trouble listing patterns. But what do you see up there? What are some of the patterns that you see?
Yes, nitrogen is fishy.
Nitrogen is fishy. So you might propose that if things have an N atom in them, that they're fishy. Now remember, this is close to the beginning of a year, that we're not introducing atoms and not asking you to memorize that N is nitrogen. All I want you to notice is that N is fishy. What else do you notice? Go ahead.
The O2 is sweet.
So see that? O2 and O2 is sweet. Okay, what else?
Things that end in 8 are sweet.
Okay, so you see that? ATE, ATE. So maybe there's a pattern to the names and they're not absolutely random. You know how hard it is to learn random names? When they have patterns to them, they start to make more sense. What else? Go ahead.
The molecules with the most number of carbons are minty.
Oh yeah, see that? C10, C10. Now by the way, we're going to make a whole bunch of hypotheses here with the students, and some will hold up and some won't. Okay, because this is a very small data set, but that's okay. We'll refine it and we'll throw the ones out that aren't so useful. What else?
There's a single O, it's minty.
Okay, single O is also minty. What about the names?
Or O-N-E.
O-N-E. But tell me something about the, first of all, something very obvious. What elements are involved?
Carbon, hydrogen.
They all have carbon and hydrogen. All right, very obvious. So a lot of things that are smells are not going to be lead or iron. Okay, they're things that have carbon and hydrogen. But what else? Look at the
More
ratios.
hydrogens than carbon.
More hydrogens to carbon. That's an important thing to know. Makes it a whole lot easier to draw structures if you know that. Okay, what else?
Sweets have double the number of hydrogens.
See that? 7, 14, 8, 16. Don't know whether that will hold up. But there's one other one that's really interesting. Look at the numbers of hydrogens. They're even, except for the fishy one. All right, so for those of you who already know something about molecules, you can already start to think about why it has to be odd if there's one nitrogen. Okay, just if you can draw the Lewis structures for that. So anyway, we engage them this way. All right, next day. Okay, what smells do you predict? Well, what do you think?
Eights are going to be.
Okay, you think they're all sweet? Well, I don't know. These two look at these two.
Yeah, they're the same. I'm going with the name thing.
You're going with the name thing? Okay. So what I would want from you is your reason. Why are you going for the name thing?
Because the 8s last time smelled sweet.
Okay. And would somebody like to have a counter hypothesis on that one? Go ahead.
Last time the O2s were sweet, so I think they're all going to be sweet.
Okay. And so those are both valid hypotheses to make at this point. Okay, this was really where the word putrid had to be taught, okay? And you've never seen anything until you've seen a whole class of high school students going, anyway, yeah. So we're not wrong. I didn't try to trick you, all right? Many O2 molecules are sweet. That's not the point here. But sometimes, I obviously have to know something else, right? Because sometimes O2 is putrid. So what else might you like to know?
What's the difference in the structure of that C4H8O2?
And they immediately go to that. How, they must be connected differently. All right. Do you see how they're getting to smell things, they're having tangible experiences, and we're motivating the next step. And so the next step would be to show the molecules. They don't know what the lines are. They have no idea what this is. But you can look at those molecules. At first, the high school teachers thought this would be too complicated, but the students don't have any trouble. So, what's the same about those two molecules? Oh, they're backwards. Yeah. Okay. Sorry. I am trying to trick you. Okay, so my apologies, the labels are backwards. But the point is, what's the same about those molecules? Because we often don't ask what's the same. What's the same? They all have a C double bond O. Where are the hydrogens? On the outside. How many hydrogens are there? Same number. How many carbons are there? Same number. How many oxygens? So they have the same formulas. All right, but what's different? You can see where this group is, which is the ester group, and where this group is out there, okay? All right, now I'm just going to take you one step further. I'm adding one of the nitrogen compounds, all right here. So I want you to tell me what patterns do you see in carbon, hydrogen, oxygen, and nitrogen? In all those molecules. What do you see? You don't really know what a bond is yet, so tell me how many lines they have. O has 2 lines. Does everyone see that? Does everyone agree with that? So how does it have 2 lines? It has 2 lines sometimes. In all of these it has 2 lines that way. Okay, what else? Oh no, O has 2 lines that way also, right? But it has 2. And what about hydrogen?
Has
1. And what about the nitrogen?
3.
And carbon? 4. Always. All right, well, for now. Some of you know more, I know that. But here's the rule. It's called HONC 1, 2, 3, 4. Okay, HONC 1, 2, 3, 4. I can get any high school student, exactly. I can get any high school student to, I don't care how weak or how strong you think they are, to be able to write correct structural formulas for organic molecules in a 50-minute period, all right? Now, that's a great start. So now if you want to do Lewis dot structures and start to understand other things, fine. But now I've got the basis for what I'm trying to think about, and I already have some connection that the way they're connected together is giving very different properties, at least in my nose, right? And so these are the kinds of situated learning and connections that we're trying to work out so that chemistry, first of all, is much easier and just much more useful to everybody because you can see where you might be able, where it comes into play in your lives. We never teach functional group names, but the students are very proud that they can read the labels and go, that's an alcohol, I know what that is. And so they learn all these connections, and if they want specific things, of course, they can just Google it. So we don't need them to memorize all these things. Okay, well, how much time do we have just to make sure? About 15 minutes? Okay. I'll just give you one more fun one, just so you can see where this whole unit goes to. At this point, we're smelling some nice ones again. We've gotten rid of the putrid smells. We have citronellol, geraniol, and menthol. Okay, here are their structures. So some hypotheses that you'd like to make about which ones smell the same? You think they all smell the same? Go ahead.
I think the menthol and the citronellol probably smell different.
Okay, menthol and citronellol probably smell different. And why do you think that?
This is the same formula, but structure.
Structure different, so we just learned about that, right? But what else? What's conflicting here? So they all end in one O, so shouldn't they all be minty? Okay, so maybe we have to refine that hypothesis. And the other thing is they all end in OL, so what's the common group that they all have, or the common connections? OH. And so this is actually leading us, we're now finding, and again, we're not wrong about O2 and putrid and sweet. But what we're finding out now is maybe there's some more things that go on. And actually the next part of this is that these molecules aren't flat like they're drawn there, but they have shapes. And for these molecules, depending on their shape, they have distinct odors. If they're long and stringy versus kind of flat versus ball-shaped. All right, and so we get, that motivates us into the structures of molecules beyond the flat shapes. And then they end up with this nice smells summary chart where we've looked at molecular formula, we've looked at the functional groups, we've looked at shape, we've looked at chemical name, and we've got a big picture of what's going on. We know what we know things that we don't understand, there's more to learn, but this is a unit that really introduces how molecules and properties are related to one another. Any questions on that? All right. So what I want to turn to now is bringing this up a level and what the next issues are. So we have this nice curriculum for the high school students. And so now the question is, what do you do when you get college students in the intro class? Okay, so did I forget to tell you how many students are in that class? All right, so you guys are really lucky here that, you know, your largest classes are really reasonable size, but these are huge. And they're in 3 lecture sections and 45 labs. And here's just a breakdown. We have a very large Asian population, and females have gone up to 60%. What's very exciting to me is that I actually teach the course collaboratively with a couple of other faculty, and what that has allowed us to do is share ideas and build a set of lectures that all of us are proud of, instead of me struggling on my own and then trying something out and it doesn't quite work. And so we've got a nice foundation, and as new people come in to work with us on the course, they add new ideas. And so this has been really a wonderful way to approach teaching. It might not have been so clear in the high school chemistry curriculum, but it is very clear in what we do in the general chemistry course. Chemistry is not about chapter 1 through 59, or what's not that many chapters, but you know, where each chapter seems to stand alone. We have chosen 4 main themes, and they're right here. And they're roughly a quarter of the first semester. So we talk about matter. And very much like we just did with smells, how can you understand what are the types of molecules in the air? Why can I walk through the air? What's blowing on, what's hitting my face when there's wind? Why can I put my hand in a glass of water and pour the water? Why can't I put my hand through this desk? So what does it tell you about how the matter is constructed, how the atoms are held together? We then go to change, where we talk about how this matter then can undergo changes, and we can build other things, and we can get other properties when we put them in solutions. This is where we deal with some equilibrium ideas. We then do energy and try to help students understand how energy is always associated with change. And we end with light. And what I mean by that is we say, so how do you really know what's there, and how can you measure the amounts? And we talk about spectroscopy and expand how instruments can expand what you can see. And we build a little bit of quantum chemistry in there, not as the the section itself, but as a way to understand why we have color, etc. And then we have really worked hard to change our class structure around. So students are given pre-class assignments that anybody in the room should be able to do, because you're just looking for patterns and you're getting ready for what's going to happen in class. And whatever observations or data I give you, we're going to use it in class. And then in class, we definitely start with data first. In other words, just like I had the students smell some things, we would provide some information. That's what data or observations, or a demonstration or some laboratory work to get you first exploring and thinking about the material. The lectures come after we've talked about the data. We try to be as interactive as possible, given the large number of students. We actually use a tablet PC where part of the slides are given to the students in advance, and then we make notes of really important things, and the students can make notes on what they have, so they can do a combination of writing some things down, but also having an opportunity to listen and not just be scribbling everything that's on the blackboard. We have lots of resources for the students: discussions, office hours, study groups, study guides. And I'm going to say more about how important the transition from high school to college is in terms of accessing resources outside of the interaction with just a textbook and the lecture. And then we do a lot of giving you lots of chances to check yourself. For those of you who don't know what iClickers are, there's response systems where you can vote A, B, C, or D. I can instantaneously show who voted what, and then if there's problems and if everyone gets the right answer, they all go yes. And if they don't all get the right answer, we can have another opportunity to discuss the material to try to understand it. We do online homework. We heard some things about that today, and from the students here. And then we have exams, and I do want to talk about the exam questions. So now, we did a study, because I wanted to understand as much as I could about this very large class, and how could I help the students in this class as best possible. So we did that by tracking the students in the class. We tracked their test scores. We tracked how they responded on a survey several times during the semester. And then we took about 60 students and interviewed them 3 times to try to track what was helping, what wasn't helping. And so that's what I want to end with tonight, is just to give you an idea of what we've learned is most important, at least to the students that come to UC Berkeley. Let me begin by talking about the assessments. And by assessments, I just mean exams. That's the cool education speak for a test. Okay, so the assessments. Here's the problem with the assessments we do. And I used to be very good at them. I would tell you what I wanted you to know. You would tell it back to me. You'd get a high grade. You'd feel good. I'd feel good. We all go home, and it wasn't clear whether anyone knew anything. So the norm, this is because they're norm referenced. And what I mean by that is, and some students can get particularly annoyed by this, that you're compared to other students. All right, so you're looking for some kind of distribution, and you say these people have A's and these people have B's, and anoint students in that fashion. But let's say Joe had 88% and John had 85% and Julie had 87%. Okay, so I guess she's better than John. So do they all know anything? Do they all know a lot? Or do they all know a little? I have no idea, right? There's no scale here whatsoever. I don't even know if I wrote a good test. I don't even know if the questions made sense. Okay? I don't even know if some of the questions everyone got wrong because I had an error in it and I didn't even know about the error in it. All right? So these tests don't really tell me what I'd like to know about how students are progressing in their understanding. And so if I want to test higher order thinking in chemistry, that's what I'd really like to know, is how are the students from my class progressing forward in terms of understanding that they're going to take with them over the course of their careers, something that's going to be useful that they can use. So what we've been working on, I don't have time to go through the details because this is actually very challenging to do, is to try to design criterion-referenced assessments. Now, as chemists, we all understand a scale, okay? Expanding a liquid, how does that tell you the temperature? Because you have it calibrated, right? I mean, it's the strangest thing in the world that you can take a thermometer all over the place and you can watch how much the liquid expands and you know what the temperature is. How'd you do that? You know where 0 degrees is and you know where 100 degrees is, right? Water freezes, water boils. So that's what you'd really like to have. And so what we're trying to develop in our scale is all high school students actually come in with lots of ideas. So they have lots of notions about things. This is their own understanding that they bring into the classroom. And by the way, at the beginning of the year, high school students will write a lot about what they understand, and by the end of the year, they will write hardly anything. It's interesting, because they're worried now that they're trying to speak a new language, and they're worried they don't understand it so well. And so that's kind of an interesting observation that we've made. But a lot of the questions that we ask students are here at this recognition level. Do you know which element S is? All right? Or, and if you look at a question, an algorithmic mathematical problem, even if it's a really difficult one, if it can be memorized, it's just simply repeating back what you've heard before. And so we think of this as our lowest level. We then move to a level where you want to know, how are things connected? Do I understand if the pressure goes up, what happens to the volume, and what has to happen to the temperature and the number of, how are those things related? How can I start to think about those? Not as a formula, but as an understanding. And then finally, at our A level, do you really understand the limitations of the models, how to use them? Can I give you new data, and can you explain something to me? And so we've worked really hard to try to make our tests roughly a third like this, a third like this, and a third like this, so that we really can push students to show us some of the simpler things that we know, but to push them to higher levels. And a lot of this is analyzed using item response theory for those of you who actually know some of the methodologies that you might use. But let me just tell you about the characteristics of the exam questions. Okay? So, they can't be memorized. All right? And I'm getting better and better. I can write questions that you've never seen before. But what's important is they're not trick questions. So if you see the answer, you'll say, oh, I get it. So it's not like that was a trick, but it's one that you couldn't have memorized. They require application of simple models and ideas, so I have to be very clear what the simple models and ideas are. But what I do is I provide data and observations, and I ask for explanations, just like you saw, just like we were doing before, only a level up. And like I said, I try to have an equal mixture of these questions, and I try to make sure that the questions themselves are valid, and we have to do partially multiple choice and partially free response. And I just want to say one quick thing about this. Multiple choice we give partial credit for, so we have lots of answers that are kind of correct, and we want to give students credit for that, and we don't have a choice because we have so many students. We can't do it all free response. But for the free response, we really just divide it literally into 4 piles. No answer, this is a great answer, this is partially correct, and there's a little bit here. All right, and we don't agonize. Maybe this one's a little better than that one. And that really gets us pretty far. And here's the interesting thing. If you do lots of mathematical algorithms, this is especially for the chemistry teacher, if you do lots of mathematical algorithms, and you will spread the students out like this, okay? If you ask them open-ended questions where they have to explain everything, you collapse the whole scale down to this, because it's not something the students are used to doing. And then we help the students get used to that, and they really excel at it. But they have to have practice and support in doing that. And what they're really doing is using the ideas. All right, so where I want to take you now is just through the 2 measurements that we did. So we have their course grades that are based on exams of this type. And we gave them, the students, beliefs and perception survey. And in particular, we asked about their academic ability. Did you believe that you could do well in the course? And then we asked them perceptions of classroom equity. Did you feel like you could do well in this class, or you feel like you're an imposter, you don't belong in this class. And then what are the perceptions of the external support structures? And we also collected demographic data. Okay, so of these three things, anybody want to wager a guess as to which is the most important for our students at Berkeley? Any ideas? By far, no, hands down, it's the belief in yourself. By far. And I didn't know that. That was actually a surprise to me. So if I look at course performance and what students report about how they think they're going to do, that's what correlates. Perceptions of classroom equity might have some positive correlation. In other words, if you feel you're being treated fairly in the classroom and that you belong, you'll do better. There's a little bit of that. Perceptions of external support structures. Look at this. Goes the other way. And the reason I think that is, but it's only of possible significance, is that if you're the first in your family and you're trying to make your family proud, you don't give up. You're going to make your family proud. Whereas if you come from a family where everything's okay in the family, and oh yes, I know chemistry's hard, don't worry about it. That's one hypothesis that we have, but we're not sure. But this is the big one. And this, the important thing here is, do all the faculty even believe that everybody can succeed? Because I think they can. And I think the faculty, first of all, have to believe that, because it's about time on task. It's about effective studying and how to learn how to study effectively, as you're going to see in a moment. And just because you think someone's smarter than you because they're using big words doesn't mean that they're smarter than you. Maybe they don't even know what those words mean. That's one thing that you learn pretty quickly. And maybe they just had more opportunities. And when you have those same opportunities, you can do just as well. But if students don't believe in themselves, they actually underperform, I think. Now, here's the one other thing that I want to talk about is we did interviews. And we asked students what resources they were using and meaning how they study, and what were their study strategies. So we interviewed quite a number of students. 2 graduate students did this. It's kind of impressive to sit that many times with that many students. And what we were very interested in was the students were willing to come and talk. So we weren't sure, we thought we'd have to bribe the students, but they didn't. They wanted to come and talk about it. And then one of the things that we got worried about is just by talking about it after the exam, the students were going, thank you, that was very helpful. And the researchers are going, no, we're just supposed to measure what's going on. We're not supposed to be interfere in any way. They're just trying to observe. But the students were really forthcoming. And we ended up coding them by their use of resources. All right, so this is the transition, especially from high school to college, but you'd hope that maybe high school students were doing this too. So when we asked them how they were using resources, meaning the textbook, meaning study groups, any video that might come from the course, using the web, going to tutoring sessions, going to office hours, here's what we found. The students who were the poorest performers were memorizing independent facts, and they were really asking, what's the answer? Give it to me. Okay? I just need to know it, just give it to me. That was their approach. And if they didn't come out of this, they really performed very poorly. The next group, where a lot of our students were procedural, meaning that they were taking in information and making small connections. They were still relying on others and the course materials, but they were at least asking, how do I do this, as opposed to just give me the answer. The students who were very successful move into this category where they're starting to evaluate information, questioning why. They're starting to talk to others because they want to go, let me explain this to you. Does that make sense? Did I explain that properly? Or do you understand that? So they started to reverse the role and believe in themselves that they could actually figure this stuff out. They could generate the information. They could explain it to other people. And then finally, we have very few who get up here here, they're really walking around literally and saying, well, how does this apply to what I see in the world around me? And they're looking all over the place and wondering how they could use the information in the class and relate it to things that they were observing. And so we saw students over the course of the semester. This is interview 1. You see almost nobody's up here in level 4, and the numbers in 3 are very small. But what you see is at interview 2, we're starting to decrease the people who are just memorizing. We're moving more people into looking for procedures. And by interview 3, by the end of the semester, we actually moved a reasonable number of people way beyond that. And you could see it in their test scores, of course, which just kept going up and up and up because of their behavior. So the summary of the findings is that beliefs about learning science are a positive predictor of what resources you'll use. So if you don't believe in yourself, you think you have to just get the information, as opposed to you can participate, you can figure it out on your own, and then you can work with others to explain what you understand. And then use of resources, if you're not using the resources at a higher level, when you do, that's a positive predictor of the course performance. And in this case, the students reported that they made changes because of the exam questions. Okay, so the exam questions only require memorization, and that's where it stays. And so just to summarize then, what strategies are most effective? Students who improved became active learners. They didn't just read the book and outline it. In fact, we stopped using a textbook because students were spending a lot of time outlining, and we really wanted them to use the textbook as a resource when they had questions. They start to work with peers, and they began to ask a lot more questions, and they weren't afraid to ask those questions. And the students who didn't improve, they stayed passive, they stayed focused on reading the text, they weren't very reflective when studying, and they studied alone very often because they didn't want to hold others back. And the best thing you learn when you work in a group is that when you have to explain things, people aren't so far apart as you think they are in terms of their understanding. I'm still learning general chemistry. And what prompted the changes? It was the exams, it was the questions that were asked, made you apply the things you were learning, and you could not memorize an algorithm to solve it. And so the idea that I want to leave you with is that I think, first of all, we need to engage students differently. We need to flip around the classroom and cut out the lecturing and get the engagement first, and lots of data and observations and contexts, or at least situations that help students connect. But most importantly, we need to get better at writing exams that you want to teach too, because they promote learning. Okay? And with that, I just want to acknowledge that I have a team of wonderful people that I've collaborated with through the years, and the National Science Foundation has been one of the groups that has supported a lot of the research and development work that we've done. And with that, I want to thank you for your attention. I went too long. Oh well. And now I think there's the microphone, right? If anybody has a question to ask.
Questions?
How do you begin incorporating this sort of curriculum into high schools where you have states that have a set list of objectives that are then tested on at the end of a year, at the end of the semester? How do you begin incorporating this type of learning into that classroom?
So this is a great question, and what we did was we decided that we would step as far as we could without stepping so far that we wouldn't be used. So we meet the standards, all right? So those state standards are all in there. And we see students quite successful. So you have some idea that, I just have to cover it again, this idea of covering. So then they don't get it, and you don't go, maybe I should do it a different way. You go, no, I just got to do it again, because we really believe that this telling works. So we have incorporated the standards, and some of the ideas that are in there make it so efficient that it doesn't take more time. All right, and the students, and by the way, students who are engaged in a 50-minute period, for example, as opposed to nodding off or looking at the ceiling, are learning a lot more, right, if they're talking about chemistry. So that, I don't know if I would keep all of chemistry the way it is, but I don't think we can just change it and go over here because, for the reason that you said. So hopefully someone will build from there when people realize that some of the materials don't need to be any longer in the course. But yes, the state standards. Okay. Up there. Part of it is universities, colleges and universities need to get more involved with the states in terms of what those standards are. I've been working with AP, by the way, and you're going to see a new set of criteria for the AP course, which hopefully will drive things. Go ahead.
What do you do for students with learning disabilities?
You know, I think this different way of learning, because we have lots of different ways that you can do this. You can go look at the webcast, slow it down, take notes on it. We provide animations that you can go out on the web and look. So if you like it to do it visually. I actually think moving away from the single mode of the lecture really does help everybody. And then of course we accommodate on tests and whatnot, and we try not to make things timed because they're rarely timed. The one great example I'll give you is there's a district in El Paso, Texas, where the students are using the Living by Chemistry curriculum, and they're all talking to one another in Spanish, even though the curriculum's in English. But because of the hands-on nature of it, it's a lot easier to grasp, even if you don't know all the English language. So, anyone else?
I have one. Okay.
It's a steep, not too fast down the steps.
So you mentioned webcasting and some other things that appear to be support mechanisms for the instructors in the general chemistry class. So tell me some things that you have available to you that help you perform better as a teacher, or that students can do to review the material or whatever.
Okay, so we webcast, meaning that somebody is videotaping my lecture and it's then available to the students. And so what the students can do is slow it down and take notes, okay? But here's what I can do. Next year, when I'm ready to teach the same class, I can go watch myself, and you haven't had much worse of an experience than doing that. And you know what? You start to go, oh my God, did I really say that? Or, oh, that stutter, or that or whatever. Now I've got to get rid of that, or pacing around. So it's really a great way to improve. And then the other resource that we have is, because we're collaborating, my two collaborators come to the 9 a.m. lecture, imagine this, and then they take notes because they do it later in the day, okay? But I get all the feedback as being the first person. Wow, why did you do this, or you forgot that? But it's been wonderful. I mean, it really is so much more fun. I mean, we're happy. They come in the morning. We're thinking about things. We have new ideas. So.
Tell me some resources the students have.
Okay, the resources the students have. So they have webcast, study groups, very important, because if you get into the right study group, you can really help each other. We have office hours. A lot of students come to the faculty office hours so that the interaction isn't so personal, but they can at least hear what other students are asking, and they can hear the way we're thinking about it. The teaching assistants have office hours. We offer a study guide, so rather than saying, read this chapter, we actually say, this is what the lecture was about today. Go back and look at some of the slides that we did and think about this and think about that and try this. And then we offer at the end a challenge problem and say, why don't you discuss this with some of the people in your study group? And then we finally end up with just a list of vocabulary words, and we go, any textbook on the web, go look it up. Go, if you don't understand what the words mean and you haven't, you'd like to know more, go look around. So we're trying to make it less memorize this little chapter in the textbook and more try to understand what the main ideas are. Does that get there? Oh, there's down here too. Herman, down here.
How have teachers been responding to this, and how are you going about getting them to change over to this way of teaching? Because it seems like they're going to have to do a lot more work and preparation for the same amount of money.
So I would say 10, 15 years ago, when the materials that lots of people got interested in developing materials. I would say when those materials weren't as well thought out, there was a lot of resistance. And so you'd always come and there'd be a couple teachers that would be go, well, you know, what we've always been doing, what's wrong with that? And we're so wonderful and we should just keep doing this. That has changed over time. So first of all, there's more students taking chemistry. So it's a broader pool of students, you know, that aren't all high-end. It used to be very few students take it. Now many students are required in some states to take it. And then you've got teachers who are teaching for the first time, and then you've got teachers who don't have a lot of chemistry experience teaching. They couldn't be happier, all right? Because the worst thing you do to a first-year teacher is give them 3 preps, and do you want to know how exhausted they are after the first month of every night trying to figure out what they're going to do tomorrow? So this is like nicely laid out for them. It tells you where to get the materials, what to weigh out. Here's the worksheet, give it to them. So you could use it at that level. And we're seeing now at the NSTA, the National Science Teachers Association meeting, very large groups that attend our workshops, and they're really excited to try new things. So I think the community is slowly realizing that, and actually high school teachers know, that it's not working what they're doing, and they're looking for ideas. So it's going to take a while. And cost we tried to pay attention to by making a lot of the labs that we do are cheap, or I've been in classrooms that don't even have a hood or don't have a lab space, don't even have a sink. They do things out in the parking lot. But yeah, that's a good question.
Question here.
I just had a question about online homework. I know you said you talked to some students about that earlier.
Yep.
But is there any other benefit aside from saving time for teachers? I mean, obviously you can't grade 400 to 500 papers a week for homework.
So don't give up yet on the online homework. So first of all, there's a couple of things with the online homework. One is, yes, you don't get a very thorough grade on online homework when you're in such a large class. One advantage, if it worked well, would be that you would get immediate feedback. Okay? And the other thing that we find is, first of all, we use OWL, O-W-L, and we set it to mastery. So OWL has a rich enough set of data that you can actually try it multiple times until you understand it, and then you can go to their tutorials and do it. Still, it's not really asking often the kinds of questions that I want to ask. But one advantage that I found is that I'm not spending time on the really things that are actually rather simple. You may not think they're simple right away, but things that are easier learned on your own, and I'm spending more time on the harder things. So I feel like our conversations have gone up. But I would agree, those systems need to be further developed. They're frustrating. They count things wrong that are right. They have wrong answers. But sometimes the system's wrong, right? I mean, students often think everything they're told is right. So it's actually good to say, no, that's a wrong answer. I know I'm right, and that one's wrong. But hopefully they'll develop better. But
Take another question.
there's a couple more over here.
Bill,
3.
then Amar, and then we'll wrap it up.
No, and then the dean.
Could you talk a little bit more about study groups and how do you facilitate those, or are the students left on their own?
So I think study groups is really hard. So this year we haven't been doing very much. Last year we tried to get some of our better teaching assistants to actually run study groups, and our Student Learning Center run study groups that are actually reasonably effective, but we didn't think it was enough. But what I'm starting to learn is that the students are actually doing it on their own. And I think what we're trying to do with the study guides that we give them is facilitate what they should be doing in their study group. And we even give them very simple ones, like you take lecture 1, you take lecture 2, you take lecture 3, and you got to ask us you got to explain it to us and then ask us questions about it. And so we're trying to pose really meaningful ways that the students might come together. But I think it's really challenging, especially when you've had bad experiences in study groups in high school. But
at Drexel, I introduced oral exams for the PChem. There were 35 or 40 students, spending half an hour with each student. First give them 4 or 5 questions and give them 20 minutes to prepare their thoughts, and then come and talk to me, and they found it very helpful.
Not only helpful, that's a way that you really do understand what the students understand. So we have, graduate school has oral exams, and we often go, it's only about general chemistry, and then we're surprised that the graduate students don't know about general chemistry, but somehow we think the general chemistry students know general chemistry. But oral exams are great, but they're very time consuming. Right?
Oh yes. I used to spend 3 days, Friday, Saturday, Sunday.
Yeah. Yeah, that's very admirable. But that's why the study groups, getting the study groups together is really important, because you can hash these things out then with one another.
Did you say there was someone else?
No, I don't know. Okay. No.
Let's thank Dr. Stacy for his talk. We have a talk tomorrow about materials chemistry. Nanowires will be the focus of the talk tomorrow. That's at 12:30 in this room. And so we're looking forward to another talk, a great talk by you. Thanks again, Dexter and Joanne, for your service to the university. And thanks to everyone who came out to the SQUIB lectures this year. And we'll look forward to seeing you again next year. Thank you very much.
Thanks. Okay.